Now topic is registers organization 8086. So there are set of registers are available within the microprocessor. The purpose is the they hold data, they hold offset address of data, they hold base address of the array or string, or they hold intermediate values or intermediate results during the calculations, just like variables in the higher languages, C, C++, Java languages, right? So here we have three categories. First category general purpose registers, special purpose registers, and segment registers, right? When coming to the general purpose register, there we have 8-bit register AHAL, BHBL, CHCL, and DHDL. So these registers combined together, they can be used as AX register 16-bit register, BX 16-bit register, CX 16-bit register, DX 16-bit register. And we have other set of 16-bit register base pointer, source index register, and destination index register, right? And now look at general purpose registers, right? So AX, it is a 16-bit register. You can use them as two dual register AH and AL, right? The purpose is temporary storage of data or holding intermediate results. So it can be used as an accumulator. So accumulator means, so after performing any operation, result is again back to the AX register, right? Suppose you divide AX by BL, so you will get quotient and remainder in the AX register itself. So remainder is available in AH, remainder is stored in AH, and quotient is stored in AL. Suppose you are multiplying AL into BL, so you will get product, 16-bit product, that is again back to stored into the AX register. Suppose you are adjusting your decimal addition result or subtraction addition results in decimal form, right? So after adjusting, again result is stored back to the AL itself. Similarly, ASCII arithmetic instructions are there. After performing operation, result is again back stored to the AX register itself. So this is what AX is called accumulator. Similarly, lookup tables. From the lookup table also, whatever value you get from the lookup table again back to stored into the AL register itself. So this is about accumulation, right? Now coming to the BX register. So what is BX register? BX is nothing but it is used as a BH and BL 8-bit register. It can be used as also 16-bit register. It can be used to temporary storage of data or intermediate results. It can hold the offset address of the data or array also, right? So it can be used as a increment counter or decrement counter for implementing the loops. Suppose we have move bx, 100h. So decrement bx and jump if not 0. Right? So if you write in this way, you're decrementing every time bx. If it is not 0, jump to here. Whatever instruction within this box, they are executed 100 times. So in this way, to maintain the loop, so bx can be used as increment counter or decrement counters. Now coming to the CX register, it is used as a individual CL and CH 8-bit register, or it can be used as a 16-bit register. Purpose is temporary storage of data or intermediate results. So it can be used as incrementing and decrementing counters for the loops. Right. Now coming to the DX register. So it can be used as a two individual 8-bit register DH and DL. It can be also used as 16-bit register. So purpose is it can store temporary data or intermediate values while calculation. It can hold the offset address of the data. It can hold the input device port address or output device port address, right? So it can hold the dividend and hold the dividend and also higher byte for the division, right? So it can hold the higher product of after multiplication, right? Or it can hold the remainder after division also. Before division it can hold the higher byte of the dividend. After division it can store the remainder of the division. It can store the higher product of the multiplication. So that is about the DX register, right? So we missed what we call SP base pointer register. So base pointer register it can be used as temporary storage or intermediate results. Intermediate to result, and it can be also used to hold the offset address of the data within the stack segment. Within the stack segment, only for stack segment. Now coming to the source index register, it can be used as a 16-bit register. It can be used to temporary storage of data or intermediate results. So it can hold the offset address of the data in the data segment. It can hold the offset address of array in the data segment. It can hold the starting address of this offset address of the starting address of the string in data segment. So destination index register it can hold the it can be used as 16-bit register for storing temporary data or intermediate values. It can store the offset address of the data within the extra segment, only in extra segment. It will work in extra segment only. It can hold the offset address of the string in the extra segment or offset address of the array. It can be offset address string in extra segment. So this is about that destination index register, right? Now coming to the special registers, special function register. First one is instruction pointer IP. It is a 16-bit register. It holds the offset address of the next instruction within the code segment. IP is always added to the code segment register to 20-bit physical address to get the instruction byte. It cannot be accessed by the programmer. And next point is the stack pointer. The stack pointer it is a 16-bit register. It can be used as a temporary. Can be used for temporary data storage or for holding the intermediate results. It holds the offset address of the data. It holds the offset address of the last entry in the stack memory. So in the stack memory, so data entered in this first data, second data, third data, right? So the last entry, the fourth entry. So fourth entry top address is FF9. Stack pointer points this address FFF9. For initial it is FFB. For every entry stack pointer is decremented. So in this way stack is increased in this way. If stack is decreased, when you remove any entry from the stack memory, suppose fourth entry is removed. Now what is the top of this stack memory? FFB, right? So stack pointer is incremented. For removal, stack pointer is incremented. For entry, stack pointer is decremented, right? So this is about stack memory, right? The stack memory, while calling subprogram, while calling a hardware subroutine return ISR, the return address is entered as a new entry. While return from the subprogram, while return from the ISR, that return address which is saved in the stack memory as a entry that is removed. Right? For each entry, stack pointer is decremented by 2. For each removal of entry, stack pointer is incremented. So finally you can write only one line, so it will keep track of offset address of the last entry. Now coming to the flag register. Flag register, what is flag register? What is flag register? The flag register is 16-bit register. It is an individual flip-flops. Flag register nothing but individual flip-flop. They are set or reset according to the result. Right? These flip-flops are called flags. Right? So what are the flags we see here? The carry flag. The carry is generated. Overflow flag. When the result is out of range, when you are performing signed addition. Signed addition or signed subtraction.